In this video, we're going to talk about the relationship between convolution and multiplication. Let's review what we've already learned. Up until now, we've started our thoughts about signal processing by having some input signal x of t. And x of t is going to go into a system. That'll be the input to a system. And for a long time, the way that we conceptualized this was that we knew that x of t had a Fourier transform, capital X of j omega. And if we wanted to know what was going to come out of the system, well, one method was to do the differential equation, but the method that we spent a little bit more time on was to get the transfer function of the system, h of j omega. So that's the transfer function of the system. And then what we did was we combined those. And we determined that if you took the complex product of x of j omega and h of j omega, you got the Fourier transform of the output signal y. Okay? So this is, for example, if you have an input signal that's a sum of cosines. So x of j omega captures how your input signal is a sum of cosines. H of j omega captures how each of those cosines gets treated by the filter or by the system, and then y of j omega captures what the sum of cosines looks like at the output. And if you want to know your output function as a function of time instead of as a function of frequency, you can take your cosine formula and you can rebuild your signal out of cosines according to what y of j omega says. Okay, so you can just start adding together cosines according to what the Fourier transform tells you, and you'll get y of t. And this method worked really well. Okay, we have a complex product here. So because it's a complex product, that means we're going to multiply magnitudes and add phases. Okay, and that's worked out really well for us before. And then the inverse, this is essentially the inverse Fourier transform, and essentially it's just saying that y of t can be represented as a sum of cosines, and the magnitude, phase, and frequency of those cosines are all captured by y of j omega, the Fourier transform. Okay? But what I want to draw your attention to is that in the frequency space, the mechanism by which we combine the input and the system characteristic is with multiplication. Now, in our study of convolution, we've learned a new way to get y of t, and that's the following. Instead of thinking about the system having a transfer function, we learned about the system's impulse response. So the impulse response is h of t, and just as with the transfer function, the impulse response captures how the system responds to all frequencies. And in fact, we learned that if you take the Fourier transform of the impulse response, you get the transfer function. So you can see now that what I'm setting up is a bit of there's a pattern here, right? On the bottom, I have time signals I have signals that are with respect to time, and in the top, you take their Fourier transform and you see what they look like with respect to frequency. So, how do we combine, if we want to do a time-only analysis, what do we do with x and h to get y? And we actually have the answer to that now. We now know that y of t can be reached by taking x of t and convolving it with h of t. So, whereas in the frequency domain, the operation we did was multiplication, in the time domain, the equivalent operation is convolution. And this is a really, really important property. Essentially what we've learned is that if you do convolution with respect to time, then the equivalent operation in the frequency space is multiplication. So multiplication with respect to frequency. And what's really crazy is that the opposite is also true. If you take two signals and you multiply them with respect to time, then you effectively convolve them with respect to frequency. So in other words, suppose I were to take a function f of t and multiply it with some other time function g of t, and then take the Fourier transform of that product. What I would find is that that would be equal to, if I had taken the Fourier transform of f of t and the Fourier transform of g of t and convolved them. So multiplication with respect to time is equivalent to convolution with respect to frequency. It works both ways. So this is a fairly fundamental property of convolution and multiplication, and it's definitely worth spending a little time making peace with it.